We very generous, yeah. Bring you to more than us.
Okay, let's start today's class. So, hi everyone, welcome back to CS2105. Last tutorial, yay! A bit happy and sad for the last tutorial, but just happy because holidays are near. How was your well-being day and Deepawali combination? Why is this anyone doing 2103? I think people are rushing to 103. No? Then what are you rushing for? Okay, anyways, today we are going to recap the last item, which is about multimedia networking. So this topic has lots of overlap with CS2108 Intro to Media Computing. So if any of this topic interests you, please feel free to take the module. It will be offered next sem. So multimedia networking, we usually handle two types of data, which is your audio and also your video, your AV system. Okay, so your audio itself, audio in real life, the way we speak, the way you speak, these are basically built as an analog signal. Okay, you can imagine it like some convolution of sinusoidal waves. When they superpose, this will create your difference in dynamics, pitch, tempo, and stuff. Okay, so this is your audio. In real life, these are analog signals. However, your computer cannot analyze your analog signals. There's just so much you can do with this continuous data. So, what you want to do now is from this analog signal, how can we discretize this? How can you convert a continuous signal down to a discrete representation of the signal? So two methods are being used. First one is what if we set certain levels. Say we set, for example, 2000 levels. Then we see for each point, which one is closest to which level. Then we take that level instead. So that process is called quantization. You try to separate it based on the levels, then you see which one is like the closest level to that current point. Okay? Your second method is, you can't simply take every single point here. Okay? Since it's continuous, anything between, for example, 0 to 1, this has infinitely many points. So at some point, you have to specify a certain interval, how many times you are going to actually quantize this data. Okay? The amount of time, the interval that you're actually going to take data, find the lowest level, take data, find the lowest level, this is what we call sampling. Okay? So you try to sample the data, cut this off how many points you're going to take, and every point you're going to quantize it down to which quantization level. Okay? So that process is actually converting analog signal down to a digital representation of that signal. Okay? Any questions? So that is what we call the analog to digital converter. Then there's something called a bit rate here that's important. So a bit rate is simply your sampling rate, multiply this by the number of bits you need to represent your data. If, for example, you only have two levels, then that is only either high or low, okay? Either 1 or 0. Then that will seem similar to, like, you know, those voltage curves, like something like that, okay? So these are only two items. Just need one bit to represent, one is high, 0 is low. But if you separate it to like more levels, say 256 levels, how much data you are going to represent what is one level, what is second level? Then you will need to find, in binary representation, how many bits you are going to need. That is when we use the log 2. How many levels you need? Find the logarithm to the base of 2. Take the ceiling. Then that is how many bits you need to make that representation. Okay? Any questions? No? Okay. Then we are going to talk about video. So video itself, you already know this. These are basically images that are being shown at certain speeds. So they are basically sequence of images displayed at a constant rate. Okay? However, nowadays technologies are so big. You have, like, for example, an 8K image. Okay? An 8K video, this is one 8K. Then you have like frame rate of how many? 60 FPS, 120 FPS. So 1 second we have like 120 of these 8K items. How long is like one video? Avengers Endgame is 3 hours. You multiply this by 180 again. It will be really, really large. Okay? But all this data can be compressed to when you download a video. You only need to download, for example, like how many? 2 gigs of video. Okay? So that is when we actually try to compress the data such that we maintain, for example, the quality and also we maintain the quality, but we reduce the size. Okay? So there are 2 types of compression that is being taught in this module. So first one is called a spatial compression. The other one is what we call temporal compression. Okay? These 2 will be discussed in the first question of this tutorial. Okay? And there's an important theorem also. I think this is not covered in lecture, but I'll discuss this. So there's something called a Nyquist-Shannon sampling theorem. This theorem is being used to determine what is the good sampling rate for you to actually reconstruct your data. Okay? So this sampling theorem, it states that if a continuous signal does not have frequency components that is above half of the sampling rate, then you can perfectly reconstruct the signals from the samples. So as long as the frequency does not exceed half of the sampling rate, then you can perfectly reconstruct this. So if we try to untangle this statement, right, we can actually obtain what is the sampling rate that is suitable. That is, suppose that you don't have any frequency components that is greater than B. Okay, so B is like the ceiling, the highest value of your frequency component. So if the maximum frequency is B, then an appropriate sampling rate for you to actually perfectly reconstruct the data is simply 2 times of this. Okay? That is like a version of this theorem. So from this statement, you can actually obtain what is a good sampling rate for your function. Any questions? No? Yeah. You will see that in information theory if you are interested. Okay. Now, this one might be familiar with y'all since we are like Gen Zs who watch YouTube from our early days before Baby Shark even exists. So you will notice that in your early days, right, when you play YouTube, how long it takes to actually play a video? Quite long, right? Buffer, wait, buffer. Nowadays, it only buffer like say 2 seconds in the start, then it will just go straight unless your data go off. Okay? So it's actually quite an improvement. So in the early days, like, for example, these items, of course, they're like speed improvements, but actually what plays a lot is in this layout delay. Initially, this is what is being sent by the server. Server will send actually all a constant rate of data that's being sent. Okay? However, since your network itself is unreliable, speed is not constant, so when it actually arrives on the receiver, this will arrive at different times. And that is what we call the variable network delay here. So if it arrives different times, here for example, then you will have like certain times where this will be slower. Then there's a buffering. There are multiple buffers that is happening in the middle of the video. So to actually prevent that, what if we shift the time we start playing, instead of directly playing here, we shift it down. So instead of playing 1 frame, then suddenly buffer again. So what if we play, say, 2-second delay? Then afterwards, we wait, for example, up to like, after this 2-second delay, any frame between these 1, 2, 3, 4, 5 frames, this will already be received. So within these 5 frames, you will ensure that it will not be buffered up. Then afterwards, this will be a certain buffer time for it to actually arrive. Okay? So that is basically a streaming here. And that is made possible because your client side, your application actually stores a certain buffer that receives the data. Okay? So this buffer will receive data through a variable fill rate, which is determined by your network. But whatever that is outputting, this is going to be output at the constant playout rate. Because you don't want this to be variable, or else your video will be fast, slow buffering. Okay? So you don't want this to be variable. This will be constant. Okay? Any questions? Now, given this client-side buffering, we have 2 scenarios. First one, if the, 3 scenarios. First one, if the variable fill rate is exactly the same as the playout rate, then good problem to have. Okay? Constant fill. What if this thing is less than the playout rate? Lag, exactly. So when the variable fill rate is less than the playout rate, there's like some kind of a deficit inside the buffer. So this will constantly go small, small, small until the buffer becomes empty, because your fill rate is much slower than the play out rate. Then in that case, when the buffer is empty, then lag will happen. Okay? Now what if the fill rate is greater than your play out rate? Huh? Buffer will overflow. So in that case, then yeah, of course, the one that's received this will not be entered in the buffer lah. But that is still a good problem to have. Drink some water. Yeah, but still it's a good problem to have lah, because you'll be ensured that this buffer will still be received. Then afterwards, the data that this will need to be transmitted again lah. Okay, so yeah. Then you might say that, for example, it's possible that to prevent buffering in the middle of the video, I can just extend it to like say certain amount of time. As a child, when I want to watch a movie, don't ask me from which side when I want to watch a movie, then I will need to actually wait it for like, for example, 1 hour, 2 hours just for me to show it quite fast. Okay, that was using a 3G modem that time. Okay, so of course that is a trade-off. You wait longer, but afterwards you get like, for example, much smoother playtime. However, this is what we call your initial payout delay trade-off. In a sense that by waiting longer, playout delay longer, then you have less buffer in the middle of the video, but at the cost of you have to wait longer initially. Okay? So the trade-off is either you want to wait longer at the start, or you're okay with broken video. Okay? Either you want jittery videos, or you prefer longer delay but smooth viewing. These are your two trade-offs. Any questions? Yeah, I think understanding this topic is easy for those who watch YouTube, which I assume everyone does. Okay. Then we are going to talk a bit of your voice over IP. So your voice over IP itself, there are two types of packet loss recovery system. First one is your simple error correction scheme. Okay, how does this work? For example, if I want to send n chunks, okay, every n chunks of data, I will need to append one redundant chunk. This redundant chunk is actually containing the XOR of every single chunk between those n chunks. Okay, so if I XOR them, then I'll put this in a redundant chunk. Let's say, for example, if I put my n as 2. First one is I have, say, for example, 100. The other one is a 1010. Then from these two, I can construct a chunk that might seem redundant, but this chunk will actually be just the XOR of both of these. So this will be 1100 XOR with 1010. This will give me 0110. Right, okay. So what is this chunk used for? Anyone? How is this chunk useful? To recover the lost chunk. Okay, so if this chunk is lost, how do I recover this?
XOR that with the covered chunk.
Okay, so with all the chunks here, so if I have 5 chunks, if one of them is lost, then within all the 4 chunks, I'll just need to find the XOR of this. 1100 XOR with the redundant chunk. This will give me exactly 1010, which is exactly the same chunk as the original one. Okay, so you see that this method works if there is one lost chunk. If 2 lost chunks, then now you have an XOR that consists of 2 different XORs. You don't know which one is which. Okay, then it will generate like, in this case, it will generate 16 possibilities. You need to figure out which one is which. Okay, but yeah, this will only work if there's a 1 packet lost chunk. Okay, questions? No? Yeah. Yeah, so 1 chunk loss, yes. Sorry. Yeah, so 1 chunk loss, then this will only work. Okay, but the best thing here is, if 1 chunk is lost, then it will still remain the original quality. All the bits are still intact. Okay, now there's another scheme here. The second scheme is going to be the piggyback scheme. So this scheme is, instead of containing this redundant chunk, I will now store some kind of a low encoding representation of each chunk. So instead of storing this additional redundant chunk, each chunk will now contain a piggyback of a lower encoding. Say for example, this will be like just 101. Then after that, I expand from here. Okay, so we send a lower resolution audio stream. This will be piggyback to the next I plus 1 chunk here. Then if one of them is lost, we can actually conceal this. We can cover it using the low quality stream. So just this is 3, so I can take it and cover it here. Okay, whatever method I used to place it here might not matter for now. But basically I can reconstruct this chunk from this lower quality chunk. Okay, the one that I actually appended. So this is a piggyback scheme. And the best part here is, of course, if it's not consecutive loss, then it can cover for each other then. Unlike this one, if n chunks, you only need to, this only works for 1 chunk loss. Okay, questions? Then finally, we are going to discuss this part, which is your real-time transport protocol. So real-time transport protocol consists of 3 protocols. First one is your OG real-time transport protocol, being used for sending your stream data. Then there's also 2 other protocols, which is called your RTSP, your streaming protocol, and also your RTCP, which is your control protocol. Details will be discussed in question 5 of this tutorial. But yeah, there's also some additional data you might need to know, which is about, say, the headers of these items. The header type will give you what the media type is, whether it's a JPEG file, it's a video, and stuff. Then the others you can read this on your own. Okay? Any questions? No? Question? No? Okay. Okay, if no questions, now. Just now we mentioned that in videos, there are 2 types of compression, which actually exploits 2 types of redundancy. So what are these redundancies and how we can exploit them? Anyone? Maybe the names first. What are the 2 redundancies? Spatial and temporal redundancy. Yeah, thank you, Ihal. Then spatial redundancy, temporal redundancy. What is spatial redundancy? Why is it? And how can we exploit it? Y'all had donuts already, get your sugar rush, you know. And spatial redundancy. Okay, so yeah, so if you have, for example, a blue sky, okay, if the pixels happen to be the same, remember that when you send a pixel, it's an RGB value. Each of them is from 0 to 255. 8 bits, 8 bits, 8 bits, total of 24 bits every single pixel. You send, for example, a 1080 pixel, that is corresponding to 24 bits, you times 1080. If they are all 1 layer of blue, I can just take 1 pixel, I count it, I times 1080. That is now 24 bits plus the log of that thing, which is only 10 bits. So 10 plus 24, only 34 bits, instead of me sending 24,000 bits. Okay? So that is the benefit of this spatial redundancy. So for example, this image, I can now find whatever is similar, then I just generate how many pixels are then counted. Okay? Might reduce some quality, yes, if you take different pixels. Say if the difference is 1, then I still take the same one, then might reduce the quality. But yeah, the reduction of quality is part of compression techniques. If you don't want to reduce the quality, still can also. So it depends on how you, what are the tolerance that you provide. Okay? Now, that is spatial redundancy. Thank you, your name is? Weishen. Okay, thank you, Weishen. Then, how about temporal redundancy? What is temporal redundancy?
It's like the same thing but across multiple.
Okay, so if, for example, same thing cross multiple frames, then what do you do? You find the difference. So say, for example, this is one bird here. If the bird moves to the right, I just need to show what is the difference that it actually moves, the motion factor. Instead of having to show even the blue sky, okay, that is like how much data I save already. So temporal redundancy is, for example, this thing. I have a frame of a woman speaking. You see that the head doesn't tilt that much. The body doesn't tilt that much. The background also doesn't tilt that much, but the hands are moving. So I don't need to send data about the background. I can just send the data of what parts of her body are moving. Okay? Where are the pixels moving, the displacements? Then that will save me lots of storage. Imagine from sending these 3 times how many pixels, right? I just need to send these 2 data now. Okay? How much save I actually save? Okay? So these 2 types of compression corresponds to And when you combine them together, this actually forms part of your MPEG compression. When you compress a video to MP4, they are being encoded to actually this method of compression. That's why you can say, for example, Avengers Endgame in like how many gigabytes only, instead of like hundreds and thousands of gigabytes. Okay, so yeah, there will be additional processing also needed, say like Huffman coding, but this one is out of scope. So important thing to note is your spatial redundancy is within that frame or intra-frame. Temporal redundancy is between other frames, inter-frame. Okay? Any questions? Okay. Now, question 2. Suppose you have an audio signal, sampling rate 16,000 times per second, and you are going to quantize it to 1024 levels. What is the bit rate? Let me drink first. Anyone? 160,000, why? Mm-hmm. Mm. Yep. Okay, thank you very much, Kota. Yep. So, to get the number of bits itself, you take the logarithm of the number of quantization levels to the base of 2. So log 1024 to the base of 2 is 10 bits. Then just need to multiply these bits by the sampling rate, which is 16,000. This will give you 160,000 bits per second, or corresponding to 160 kilobit per second. Okay, so you might see this often if you do like say Premiere Pro or like Audacity items. You might see like sampling rates. Now you know what it means the bit rates okay. Now you know what it means. Any questions? Okay. Now question 3. I think question 3 is quite simple. So suppose that we stream, instead of using UDP, we use HTTP. Then there's something called a TCP receive buffer. Is TCP receive buffer the same thing as your client application buffer? Who says yes? Who says no? Hey, why is it no? Anyone? They operate on different layers, yes. So because they operate on different layers, then the roles are different. Okay, one is for transport layer, verification, processing, the other one is for application layer. Yeah, thank you, Chi Xiong. One student from my previous tutorial, she mentioned that it's no, because the question implies that it's no, because they asked how do they interact. So most likely it's a no answer. Yeah, makes sense. I had one statistics question. It was about statistics. Is this a Markov chain? Yes or no? And then you have to prove. Then the next question. Convert this question to a Markov chain. Then of course the first one is false. Okay. Yeah, so yeah. Of course this is a type of question that would rather say no. So yeah, they are not the same. Because HTTP works on the application layer, TCP works on the network layer. So they behave differently. Your TCP buffer is, as we discussed in like week 5, week 6. This is used to like maintain out of order packets, process them, do your checksums and stuff before you actually forward it as HTTP packets to the application layer. So each of these are basically your packets in transport layer. But when you receive your item in the application layer, you only receive it as like the data, the result of your HTTP request. That is a different packet already. So on the application layer, then that is basically the buffer that is being used on your rendering. Okay, when you receive the data, this will go into the client buffer for your YouTube videos, for example. So this is how they interact in a sense. This buffer for your transport layer, then this will pass, this will become your playout buffer on like your application. Okay, any questions? No? Okay. Now, question 4, logical, simple, intuitive. Why is a packet that is received after scheduled playout time is considered lost? Simple answer. Exactly. Exactly. You go to Changi Airport, you go shopping, then you saw on the TV, right, gate closed. No matter how many times you bet, you cannot go in already. Okay? So there's in fact I actually did similar last time. Yeah. If you miss a flight, then you miss already. The flight cannot just go back just to fetch you, right? Okay? So basically show must go on. If you receive a packet that is late, then what's the it will not be able to play it anymore. If it is able to play that again, that is what you call a glitch. Okay? You don't want suddenly some Mr. Beast video will be showing from the start lah. You don't want that to happen. Okay? Questions? Easy, right? Now, okay, question 5, 6, and 7 are the important questions of this tutorial, I think. So question 5. In practice, just now we discussed there are 3 real-time protocols that are under the real-time transport protocol suite. First one is your original RTP, which is being used to send your media data. Then we have a real-time transport streaming protocol, your RTSP, to be used to send playback commands like play, pause. Then finally, you also have your RTCP, your control protocol that is being used to send info about that transmission, streaming info, real-time info, streaming data and stuff. Okay, so the question is, why does media flow uses UDP, while for playback commands it uses TCP? There's a logical and intuitive reason for this. Hey, maybe why do we want to use UDP for sending the media data? Faster. Okay? It's faster, but it's unreliable. But if the data is like 60 frames per second, you miss one frame, no one gonna notice anyways. It's not like it's gonna go to Mars or something, okay? So within a certain limit, unreliability is still tolerable within our video playing. Okay? So there's a certain tolerance limit that is within okay limit okay, when you see this kind of streaming. So yeah, it's faster. How about RTSP? Why do we use TCP for that? Why do you use TCP for play pause commands? Then you want it to, when you stop, it actually stops. Okay? So you don't want the critical information to actually be lost. Critical information, when you want it to stop, it should stop. When you want it to play, it should play. You want it to restart, it should restart. It should not move on. Okay? So these are informations where reliability is important. So media flow is for sending video packets. You prioritize UDP because you need speed much better than your reliability. You don't want the trade-off here is the benefit of having all frames arrive doesn't outweigh the benefit of having the user to actually enjoy the video in less delay. Okay? 1, 2 missing frames, no one cares. Okay? No one is gonna check exactly each frame to see if it's there or not. But yeah, so it's still within tolerable limits. Say within Zoom, it's better to actually hit it fast, some missing frames okay, rather than it being slow and delayed. Okay? So in contrast, your RTSP, you want it to play, you want it to pause, this should be fast. This should be reliable. You want it to, when you click end call in Zoom, it should end call. If you don't, whatever you cast about that person will be heard. Okay, you don't want that to happen. Okay, so you should prioritize reliability over actually your speed lah. Okay, questions? Okay, so RTCP is your control protocol. This is used to obtain status info and then transmission statistics, quality of service and stuff. So actually, have you all seen this data in YouTube? Anyone tried? No? Okay, let me just demo this very quick. Yeah, so if for example you do YouTube, right, there's going to be this one settings. It's not settings. Is it info? Right click the video. Okay, I forgot already. Yeah, there should be some kind of this statistics for nerds. Yeah, this is when RTCP is used. So there's like some kind of these are like some kind of control statistics that is being sent. So why do we use UDP for this? These items you want it to be real time. If some of them are missing, it's fine. But You want it to happen like directly. You need the speed better than its reliability also. That's why it uses UDP here. Okay. Thank you for those who say right click. You are not too. I think in English it says statistics for nerds, but I think my YouTube is in Indonesian, so yeah. No offense, no offense. Okay. Question 6. So consider the figure later, which is similar to lecture 10 notes, page 26. So in this figure, the sender starts sending a packet at time t equals 1. And then when this first packet arrives, is at t equals 8. Okay, someone is streaming some media now. So yeah, when it arrives, it's at t equals 8. The question now is, we want to find, for each of the packets from 2 to 8, what are the delays in terms of the time units? So it's easy lah. You can say together. Okay, so packet 1, delay is from 1 to 8, that is 7 time units. Packet 2, 7. Packet 3, 9, 8, 7, 9, 8, 8. Okay, so yeah, that is basically the delays here. 779, 879, 88 time units. Okay, questions? Easy? Easy, right? It's just counting. Okay, so next question. If we start the playout at t equals 8, which packets will arrive late? Packet 3? Okay, packet 3 obviously late. 4? 6, 7, 8. Okay. How?
You can just draw a line, see which packets like behind the.
Yep, exactly. So you can assume your sender has this jagged line, right? Then you want to some kind of shift this item to the right, okay? But of course, in exam, it's hard to draw the jagged line. So in that case, just need to draw a straight line here. Take the left points there. Then you can visualize it some kind of moving to the right. Okay? Starting at t equals 8. Then once it moves to the right, you will see that this point meets. But this point here, these are actually missing data. Okay? So you will see that when the packets actually arrive later, then these 3 packets are missing. Your 3, 4, 6, 7, and 8. Okay? Questions? So forget the jagged line. In exam, just draw a straight line. If you kind of know the gradient already, then you can like parallel that line. Then you can see which ones are missing. Then that's easy. Okay? Questions? No? Okay, if no questions. Now, if we begin at t equals 9, which ones are late? 3 and 6. Why? 9 packets delay. Okay, so you can shift 1. Then you will see that only 3 and 6 will be late now. Okay? So actually there's a trick here. The trick is actually from 1 to 8. This is a delay of 7 time units. So any delay that is greater than 7 units is going to be late. Just find which one is 8 and 9. Okay? Now if you shift to t equals 9, this is a delay of 8 units. So any delay that is greater than 8 units will be late. So all those 9 packet delays, this will be late. Okay? So that's one way of looking at it. So now given that we already know the packet delays, what is the minimum playout delay so that all packets arrive in time for the playout? When should we start? 10. Why is it 10? Okay, so when you try to shift this to a certain amount, when it reaches 10, you'll see that none of the packets are missing. Okay? Why is it 10? You find all the packet delays. What are the time units? Take the maximum. 7, 7, 8, 9, 9, 9, 8, 9. Find whichever is the maximum there, which is 9. Then you shift 1 plus 9. Then you will know that you need to start at 10. Okay? So when you start at 10, none of the packets are missing there. Hence, we will now start from 10, and that will incur a 2 time unit delay from when packet 1 arrives. So set the playout delay as 2 from when packet 1 arrives, then you will get no missing packets. Okay, questions? No? Okay. Last question. And last question of the semester. So, recall that we discussed about two schemes. The first scheme just now for your error correction is the redundant chunk scheme, the simple scheme. Then the second scheme is using the piggyback scheme. Okay? There's a third scheme also, the interleaving scheme, which is not discussed in this tutorial. You all can read that on the lecture notes. Basically, we are going to see what are the trade-offs. When is one scheme preferred over the other? Okay? So, in the previous scheme, instead of generalizing it to n, we try to set, for the first scheme, every 4 chunks will generate one redundant chunk. Okay? So n equals to 4. Then the second one is basically, you are going to add a lower encoding rate, which is 25% of the original transmission rate. Okay? So, the question is how much additional bandwidth does each scheme require? My markers. Any ideas? So initially, say if scheme 1, if we are going to send just 4 chunks of data, then this is basically equivalent to your 100% of your initial bandwidth, correct? Okay, 4 chunks. But due to our FEC scheme, we would need to add one additional redundant chunk. So there would need to be one additional chunk here, which is just redundant. The question is, how many percent additional bandwidth is this? 25%, okay? So for the first scheme, this will require 25% additional bandwidth. Questions? Easy? So if I add another 4, then this will be 25 lah. The limit will be 25% bandwidth, upper bound, okay? Then, second one. Scheme 2 is instead of saying that I'm going to add one additional chunk, each chunk now will contain a piggyback that consists of 25% the original chunk. Okay? So we'll do something like this. Now what is the additional bandwidth? So for calculating this, actually we don't need to consider the first one. Okay? The first one we can actually assume that it has. Because in the end, if you have like a continuous amount of data for a large n, this will approach similar lah. Okay? It's just one difference. So there's a limit there. So what is this additional bandwidth? Initial data is just the black one, right? All of this is 100%. But now you add an additional 25%. 25%. So what is the additional bandwidth here? 25%. Okay? You have original chunks. Each chunk will now have 25% additional data. Okay? So that is similar to just saying this is 25% additional bandwidth. Okay? If you include the first one, then the limit will still be approaching 35% if large n. Okay? Questions? So in these two, both schemes will actually require additional 25% bandwidth. Okay? Questions? Yeah. When will this reach 25%? If you have an auntie talking another auntie in a voice over IP, 3 hours, 4 hours call, that will reach 25% now. Okay? Quite large. Now, let us assume that both schemes now have a packet loss. How do the two schemes perform if the first packet is lost in every group of 5 packets? So these are 5 packets. None of them is lost. How would this perform? First one, how do you recover this packet? XOR. When you XOR it, you will get a packet. What can you say about the quality of this packet? Is it the same as the original or reduced quality? Same, okay? Because each of the bits are going to be correct, non-tempered. How about the one below? What do we do here? How do we recover this chunk?
Use the reduced bandwidth of the limit.
We use this reduced bandwidth. We do whatever magic here in order to make this the original chunk. Okay? So 25% chunk. We use the lower encoding robotic sound. Use it here. What can you say about the quality? Lower quality. This is reduced. Okay? Hence, for the first two schemes, and for the two schemes here, scheme 1 can actually reconstruct your lost packet, your lost chunk in full quality, original quality, whereas scheme 2, it will only generate a low audio quality because it generates it based on the 25% reconstructed item. Okay, questions? Now, okay, I messed up. What if in the two schemes, instead of one packet lost every 5 packets, now one packet is lost every 2 packets? Say for example, something like this. See like this. What happens now? First one, can you reconstruct data? No. Okay. First scheme works only when you have one packet loss. If there's 2 packet loss, then you have lots of possibilities to actually generate it. Okay, unless you have like some kind of a prediction algorithm that can match previous and after, and in that case, you can generate a close enough prediction. Okay, but not the exact one. Okay, so first one cannot generate here. How about the second one? Can it generate? This one, if they are consecutive, right, then the second packet, this one cannot be generated because this chunk is lost. Okay. However, this one can still reconstruct the missing third chunk. Okay. So in that case, now you have first chunk, second chunk is lost, third chunk is reduced quality, fourth chunk still intact, if they are consecutive. If they happen not to be consecutive, then you will have first chunk is original, second chunk is reduced, third chunk is original, then fourth chunk is reduced, something like this. Okay? So in the end, it happens that there's like 2 packet loss here, and there's 2 chunk loss here, then that is the time when second one actually produces a better quality because the chunks are not lost. Okay? Simply because the chunks are not lost, or even if it's lost, it's only one loss compared to the first one which loses everything. Okay? Hence, scheme 2 will have a better audio quality despite not being original, but still at least there's some audio lah compared to it being lost in the first place. Okay? Any questions? So these are like some trade-offs that you need to keep in mind. First scheme is good in producing audio quality, but if one chunk is lost, it works okay. 2 chunks are lost, boom, you don't know what to produce. Okay? Second one, not really that good, but still reduce quality lah. Okay? So, of course, there are trade-offs. You can construct, say, a perfect item. What if you use the second scheme, but with full audio quality? Then that's the time you have huge overhead. Now you have 100% encoding after each chunk, right? Okay? So that's huge overhead. Or for example, say you do first scheme, but we reduce the n to a smaller value. Say every 2 chunks, you generate 1 chunk. Okay? So in that case, suppose if I have 2 chunks, we generate 1 redundant chunk. What is the additional bandwidth? 50%. Okay? So that is quite large overhead. So if your bandwidth is like 1 gigabit per second, then 50% is quite large. Okay? So yeah, trade-offs are there. The whole module is about trade-offs. You understand all these stuff lah, basically on, this problem, what kind of solution would you propose for that certain cases, that practical outputs, then you use it lah. Okay? So basically it's all about trade-offs, decision-making process. Okay? With that, then, any questions? Okay, if no questions, then that is the last topic of today. I hope not to see you in 2105 next time. So yeah, thank you very much for coming throughout the past 11 weeks. It's a great pleasure to meet you all. And sorry for like lots of bumps. This is like the first time I'm teaching CS2105 also. So apologies for any mistakes. And before that, I have several announcements. First one is just now. Then if you all want to take additional donuts, please feel free. Help me from getting diabetes. Please don't. Okay. Second one is module teaching feedback is open already and will be closing on recess week. So please help provide me some teaching feedback also on anything that I can improve so that helps the other iteration of students from you to actually benefit from what I teach lah. Okay. So please provide your honest review lah on what I can improve as a person, as a teacher lah. Okay. Then Third one is I think I mentioned last week, but for the benefit of those who are not here, if you are free tomorrow, please come down to steps and help vote for our project. CS2016 Group 2, this is my group's project. For those who don't know what the project is about, we are actually building a website that allows you to create a website just simply by a single prompt. Okay, so if you want to prompt out, say, a portfolio for like what, say a security consultant for cybersec, then this will actually generate you a portfolio within like seconds, okay, which is actually exportable to React code. So please try it out also. You can actually customize the styles. And the one thing I want to share today is actually currently we are having a contest for our project. So if you are keen, it just takes 5 minutes of your time to actually prompt one single prompt, style out whatever you want, then you can submit it, get a chance to win our prizes. Currently still low submissions, so high chance to win. Actually it's not listed here, but top 15 winners will actually get a free great front end annual subscription, and that is like worth about how many, 50-60 bucks. So yeah, that is like for top 15 winners. So if you are interested in front end development, please try this out. We are giving free money basically. Okay, so yeah, please help vote for us also if you can come down tomorrow. Then yeah, my last thing to mention is that from now until your exam week, I understand this is week 13, so no one studies. But happens that you're studying, you have any questions about the module, feel free to chat me anytime. You can chat me anytime through exam week or after exam week if you're a psycho. Okay? And if you need to book a consultation with me, my consultation link is also there on the Telegram group. Okay, feel free to consult me on anything. I am paid for this, so utilize your resources. Okay. Other than that, then that's it for this tutorial. Thank you very much. Thank you for coming to CS2105. And I guess before we end,